Welcome to another finite element lecture. This lecture is vibrations analysis with FEA. So far we have learned about static analysis. So this one is the first topic where we are going to add motion, dynamics to our equations, and we start with vibration as a segue into this new world. At the end of this lecture, you will be able to write the finite element equation of motion, identify the terms of the FE equation of motion, and determine natural frequencies and mode shapes of structures with FEA. So why do we need to know about this? If the frequency of an excitation matches a natural frequency of the system, which is a property inherent within our system, it can cause catastrophic failure. An example is the ground resonance shown here. So this was a test, but in real world, landing on one side can cause the blades to get unbalanced. When the frequency of the unbalanced rotating blades matches the frequency of the airframe of the helicopter, it can cause resonance. If the landing gear is on the ground when this resonance happens, and it means that the landing gear is constrained by the ground, this resonance can cause catastrophic failure, as you have seen in this test. Natural frequencies are inherent properties of any system. They often need to be considered in the design due to failure or discomfort considerations. For instance, excessive exposure to vibrations exacerbated by resonance can lead to chronic pain and injury, like I have shown here in these pictures in the motorcycle handlebar. So far in the finite element analysis, we have dealt with quasi-static problems. In real world, all loads vary with time, but in some problems, loads vary very slowly, so slowly that we can assume their inertial effects are negligible. We call these problems quasi-static. So you have seen the FE equation of equilibrium for static or quasi-static problems before, which I have shown here again. If loads or excitations vary so quickly that their inertial effects cannot be neglected, the problem is called dynamic. For dynamic problems, we have the FE equation of motion, which I have shown here, and we will discuss it a bit later. So first, let's look at a system that has 1 degree of freedom. Often we show those systems with a mass, spring, and a damper, and it's only allowed to move in the x direction. Ft here represents an external force that is applied to our mass, and it can change in time. We want to write the equation of motion using the second law of motion, Newton's second law of motion, for this system. So here is the free body diagram of that mass. So the force is applied here, and then as it moves in the positive direction, in x direction, we have the effect of the spring kx, and also we have the effect of the damper, which is cx dot. So if I use Newton's second law of motion, it tells us that sum of the forces applied to our system is equal to mass times acceleration, the forces that are applied to our system are Ft in the positive direction minus Kx minus Cx dot. They're applying in the opposite direction, equals mx double dot. Now, if I rearrange this equation, we will have this equation where we have mx dot mx double dot Cx dot and Kx, and that's equal Ft. Right, so this is the equation of motion for this mass, 1 degree of freedom system. If this force is changing like a sinusoidal wave, so if Ft is something like a magnitude sine omega t, then the motion of this system, we often call it forced vibration. If the force is applied to the system in an oscillatory manner and the function is like this, that will lead to the so-called force vibration. Generally, the response of our system to external force is determined by the nature of our system. And the nature of our system is defined by its properties that are within its nature. So the physical properties that we can see here are the mass, damping, as well as the stiffness, and also the boundary conditions. In order to learn more about the nature of our system, we use the equation of motion, what we eliminate the external force. So the equation of motion, if you recall, was mx double dot acceleration, Cx dot velocity and Kx, and on the other side we make the external force 0. This is the so-called free vibration. So when you have a system that is moving, it's in motion without applying any external force. And this equation actually can help us to learn a bit more about the nature of our structure and then how it can be utilized in our design and simulations. So for now, if we assume that damping is 0, so that would then be undamped vibrations. So if I assume C is 0, that equation will be mx double dot plus Kx equals 0, right? And this equation can have a solution which looks like this. X equals a magnitude times sine omega t. So that would be the solution for our problem, our differential equation here, where A is a magnitude that can be determined based on the initial conditions. So for now, we are not worried about that. What is really interesting is that omega here, which if you solve that, if you put that back into this equation and solve it, you will find that omega is the square root of K over M. So the stiffness over mass. Omega is called the natural frequency of this system. So as I was emphasizing, we are looking at the nature of our system, and for a good reason, this omega is called the natural frequency. It depends on the stiffness of our system and the mass of our system. So you can imagine that if we make our system stiffer, like increase the stiffness of our spring, natural frequency goes up, or if we add the mass to our system, a natural frequency will go down. This equation, although it's based on a 1 degree of freedom system, it's an extremely useful equation. It does apply to very complex structures as well, where you're looking at the natural frequency of those structures, where you want to increase or decrease the natural frequency. I have often seen that when students are solving those problems, and they are trying to increase or decrease the natural frequency, they may add material, for instance, to increase K, but they may not realize that by doing so, they are also increasing M. So this equation can really help us to better understand the relationship between Km and the natural frequency of our structure. Now let's bring that external force back into the equation. If we do so, we can have an interesting phenomenon which is called resonance. In mechanical systems, resonance is the tendency of the system to easily transfer potential energy to kinetic energy and vice versa. This happens when the excitation frequency is close to the natural frequency of our system. So look at this example for now. So you saw that by using sound, this glass was forced to vibrate. And as the frequency of sound is changed, the vibration changes. When the frequency of sound gets close to one of the natural frequencies of this glass, resonance happens. And you can see when resonance happens, it can lead to catastrophic failure and complete fracture of the glass. So the question is, how can we find natural frequencies of complex structure? Now let's generalize our 1 degree of freedom problem using the FE method. We know that an FE model can have many degrees of freedom. I'm sure that you recall that a node of a solid element has 3 degrees of freedom, which are translations in X, Y, and Z directions, and a node of a beam element has 6 degrees of freedom, which are rotations and translations. The equation of motion of a system described discretized with these elements, like finite elements, can be written like this, where M is the mass matrix, C is the damping matrix, K is the stiffness matrix, and R is the vector of nodal forces, which are external forces. D here, you remember, this is the vector of nodal displacements, and now we have D dot and D double dot, which are the first and second time derivatives of the vector of nodal displacements. Hence, they are representing, or they're containing, the nodal velocity and nodal accelerations. So let's look at undamped free vibrations now in FEA. For an undamped structures undergoing harmonic motion, each degree of freedom moves in phase with all other degrees of freedom. Thus, we can write the vector of nodal forces as a sine function. Is function of time. We have omega, which is the natural frequency, and here we have the amplitude of these nodal displacements. If we differentiate this with respect to time once and twice, we will find the vector of nodal accelerations like this. So combining these with the equation of motion and putting C and R0, hence undamped free vibrations, we will end up with an equation like this, where in this equation we know that this is the vector of this is the structure stiffness matrix, this is the mass matrix, and lambda here is omega squared, so this is natural frequency squared. So probably you remember such an equation from the buckling analysis. This is an eigenvalue problem, and what essentially we are trying to do, similar to buckling analysis, we are trying to find the eigenvalues and eigenvectors of our system, described by this fundamental equation. So the trivial solution for this is when amplitude is 0, so that's not useful. The non-trivial solution of this equation are obtained by solving the eigen problem like this, so where the determinant of this matrix is equal to 0. So now solving that equation determines eigenvalues lambda I for us, and natural frequencies are the square root of these eigenvalues. So as you can see, we have natural frequencies, not a single natural frequency. So for a finite element, we have as many natural frequencies as the number of degrees of freedom. The lowest natural frequency is called the fundamental vibration frequency, or in short, fundamental frequency of our system. So associated with each eigenvalue is an eigenvector, which you remember is the amplitude of displacements. This vector describes the shape of the mode, or the mode shape. So here is an example. You can see a few mode shapes and their associated natural frequencies for the glass that you have seen before. So essentially we have now the natural frequency here, and this shape is described by the eigenvector associated to that natural frequency, and we have mode 1 vibration, mode 2, and this is mode 3. So this one is the fundamental frequency of this glass. So you should note that imposing boundary conditions can eliminate some mode shapes. So here we have imposed boundary conditions, so we have fixed the bottom of the glass here. The other note is that eigenvalues depend on mass distribution and stiffness, as you have seen for the simple 1 degree of freedom model. Okay, now let's solve a problem by using the finite element method. So here we would like you to determine the lowest natural frequencies of this motorcycle handlebar. Assume that this handlebar is made of structural steel. Can you comment on the comfort aspects of this design? So you should then put that into the context here. So vibration frequencies between 31.5 Hertz and 125 Hertz can cause discomfort or damage depending on the exposure time. So essentially what you need to do is to determine the natural frequencies of the handlebar and see whether they fall within the range of these frequencies. And if they do so, then essentially the vibrations of the motorcycle in the operation or on long journeys should not fall in that bracket, because if it does that, then it means that resonance can happen, and therefore there could be more discomfort and possibly damage. Hence the designer can now make a more informed decision here. So I have solved this problem in a supplementary video, which I invite you to watch. So in summary, we have learned about quasi-static loading and dynamic loading. We learned about concepts of natural frequency and resonance. And we learned how to determine natural frequencies and mode shapes of structures using the finite element method. I hope you have enjoyed this lecture, and thank you for your attention.